In this video, I'm going to teach you how to calculate K, the equilibrium constant, from standard delta G. And to do this, we're going to be using the equation delta G non-standard equals delta G standard plus RT times the natural log of Q. Now, in order to calculate the equilibrium constant K from delta G using this equation, we need to do a little bit of manipulation to this equation. And before we do that, we're going to keep a couple of things in mind. So when our reaction is actually in equilibrium, once it gets itself to equilibrium, the reaction quotient Q, the numerical value of the reaction quotient Q, is going to be equal to K. So in this equation up here, we can actually substitute K for Q because when we're in equilibrium, Q and K are numerically equal to each other. Also, when we are in equilibrium, the value of our non-standard delta G is going to be equal to 0. This is one of the things that we talked about when I first introduced delta G. I told you that for a spontaneous process, the value of delta G is negative. For a non-spontaneous process, the value of delta G is positive. And for a process that is in equilibrium, the value of delta G is 0. So with these two things in mind, we're going to manipulate this equation up here. So we're going to say, if we're in equilibrium, the value of delta G is going to be 0. That's not going to be true for delta G standard. That's not going to be equal to 0. And instead of writing RT natural log of Q, we're going to write RT natural log of K. And then I'm just going to simply rearrange this equation because we have 0 on the left side, and that's kind of strange. So we're going to change it to say delta G standard is equal to negative RT natural log of K. And in this equation, delta G standard can be calculated using Hess's law, or it can be calculated using delta G equals delta H minus T delta S. R is the ideal gas constant in the form 8.3145 joules over moles Kelvin. And T, the temperature, is in units of Kelvin. And then K is just our equilibrium constant. So let's apply this to a particular problem. Let's say that we have the reaction H2O2, which is a liquid, in equilibrium with H2O, which is also a liquid, and 1/2 of a molecule of O2 gas. And if this is the first time that you're seeing a fraction as a stoichiometric coefficient, it's not very common, but it does happen sometimes, and it is valid. And let's say that this reaction is being done at 25 degrees C, and we wanted to, for this reaction, calculate the value of the equilibrium constant K. In order for us to be able to calculate K, we need the temperature, which we have. We need the value of the gas constant R, which we know, and we need to be able to calculate delta G. As I said before, there are two ways that we can calculate delta G. In this particular problem, I'm going to calculate it using Hess's law. To calculate delta G using Hess's law, delta G standard, and for this, we are going to take the delta G standard of our products, H2O, and also 1/2 of the delta G standard for our other product, O2, and we are going to subtract from that the delta G for our reactant, H2O2. These delta G values, we just look up in a table of thermodynamic data. We can plug them into this equation. So looking them up in my data table, I get negative 237.2 joules per mole for H2O when it's in the liquid phase. O2 gas is a 0. And then the delta G for H2O2 is negative 118.1 joules per mole, kilojoules per mole. So this works out to be negative 119.1 kilojoules per mole for this delta G standard. Once we have that number figured out, the rest of this is pretty straightforward. So I'm going to take this equation here, I'm going to copy it down below. Delta G standard equals negative RT natural log of K. And I'm going to start plugging in everything that I already know. I know that my delta G standard value is negative 119.1 kilojoules per mole. I know that the gas constant is 8.3145 joules per mole Kelvin. My temperature, 25 degrees C, that is 298 in Kelvin. And then the last thing I need here is the natural log of the equilibrium constant K. Next we're gonna isolate this natural log of the equilibrium constant K. We're gonna do that by taking this term and dividing both sides by that amount. So our left-hand side is gonna become negative 119.1 kilojoules per mole. And that is going to be divided by negative R, 8.3145 joules per mole Kelvin times 298 Kelvin, and that is equal to the natural log of our equilibrium constant K. It does get a little bit confusing because we have K, the equilibrium constant, and then we also have K, the temperature unit. We just gotta keep stuff straight. So we can clean this side up a little bit. Notice that we have negative sign on both the top and the bottom, so I'm just gonna erase them completely because they cancel each other out. Now in terms of units on this side, we do have some units that are compatible and that are canceling, our mole unit and also our Kelvin unit, but notice that our energy unit in kilojoules and joules, that's not going to cancel itself out. So what we're going to need to do is a kilojoule to joule conversion. And I'm just going to squeeze that into the top of this, into the numerator over here. So 1,000 joules is a kilojoule. And that is going to take care of all of our unit canceling. Our moles will cancel, our kelvins will cancel, our kilojoules will cancel, and the joules will cancel as well. And so we can work the math out on this. The natural log of K, I'm just reversing the two sides here, is 48.1, and it's a unitless number. Now remember, our goal is actually to solve for K, and the way that we do this is by taking the inverse natural log of both sides of the equation. You may need to review math to remember how to do this. We're going to raise the 48.1. We're going to raise e to the power of 48.1. And this number works out to be about 7.5 times 10 to the 20. Unitless number, equilibrium constants are always unitless numbers.